Okay, now we have to be careful with two things with the inflection point. One of the things is that the second derivative can be zero at a point that is not an inflection point, okay? And we have the same issue sometimes with our first derivative. Sometimes we get a zero, but it's not a maximum or minimum. With the second derivative, the same thing can happen. I can be curving up, even out, and then curve up again. But basically, remember that we're looking for a sign change. So if f prime does not have a sign change at one of its zeros, then it's not going to work. So what we do is we just check whatever x it is as a zero. We can check what's happening on either side of that. If I'm getting the same sign on either side, it won't be a zero. Now another thing that can happen is it doesn't have to be zero. It does not need to be zero at an inflection point. What does have to happen is there has to be a tangent line. If I have a vertical tangent line, first of all, my derivative won't exist there, and if my derivative doesn't exist, my second derivative will not exist there. But what could happen is it could be something like this. Okay, I'm increasing, I get a vertical tangent line, so my first and second derivative are not going to exist there, but I do have a smooth curve, I do have a tangent line existing there, it's just that the derivative doesn't exist there. I'm concave up, then I'm concave down, so this is an inflection point. So we have that right here. I have a vertical tangent line, even though when I take my second derivative of this, it's not going to exist, because it's going to be a zero in the denominator. With this one, x to the fourth, my second derivative is going to be x squared. And so this is always positive. There cannot be a sign change. So what's happening there, I'm going down, I'm leveling out, and then I'm increasing. I'm getting a zero here, but there's no change in concavity. This is not an inflection point. Okay, so those are two things to look out for. This one's usually the harder one to see because we kind of have to analyze the original function to see what it's actually doing to get that. Okay, motion along a line. Remember, we're connecting velocity and acceleration with our position function. And so we're looking at the derivatives of this. So my velocity of this would be my x prime here. So 6t squared minus 28t plus 22. That's my velocity. Now if I wanted to find maximums and minimums, I'm going to set that equal to 0. I can divide all of that by 2. Try to factor it. We go with 3 and 11. And yeah, that should give me what I need. So it's happening here at t equals 1, but I'm getting a 0, and at 11 over 3, which would be about 3 2/3. I'm getting my zeros at those points. I want to look at what's happening between them. So anything less than this, if I plug a 0 into that, I'm going to get a positive number. Anything between there, I'm going to get a negative number, and anything bigger than that, I'm going to get a positive number. So up and then down, this is a maximum at 1 and a minimum at this point. For my acceleration, then I'm going to take the derivative of the velocity. And so looking here, we've got 12t minus 28. Again, we're going to set that equal to 0 to see if we can find any inflection points. And we get 28 over 12, which, yeah. So that's going to be about 2 4 1/3. And even though that's giving us a 0, we still need to check on either side of that to see that our sign is actually changing, which it should be on this side. It would be a negative number. And the side these numbers are bigger, so it's going to give us a positive. So since we have that sign change around the 0, then we know that this is a point of inflection. So when they ask us to describe the motion of the particle, we could think of this negative here for acceleration as decelerating, or deceleration, and this is accelerating. In general, when we talk about acceleration, we do not talk about having a negative acceleration. Usually we want to use the word that is decelerating or slowing down because it's better to interpret that rather than just saying a negative. To do that on the AP test, they'll probably count it wrong. You just say a negative acceleration. You want to interpret it as what's actually happening. So what this thing is doing then, as we describe the motion of the particle, the velocity is positive, but it's slowing down here. And then our velocity is negative. It's still decelerating, which means we're moving backwards here. When we get to this point here, 2 1/3, should be in here somewhere, we're still decelerating. We're changing to acceleration now. We still have a negative velocity, so we're moving backwards, but it's now slowing down. Really, it's actually speeding up again. The speed is now increasing, or the velocity is now increasing, even though the speed is going down. And so we're getting back closer to zero. When the velocity becomes zero, we're going to be speeding up. So even though our velocity is negative here, we're kind of putting on the brakes, but we're accelerating. Our forces are pushing us in the positive direction, even though we're not moving in the positive direction yet. Okay, now this next test, the second derivative test, is dealing with maximums and minimums. Before, when we dealt with maximums or minimums, we knew that we would only look at f prime. And we were looking for a sign change. We would start by saying f prime is 0 here, it's positive here, it's negative here. But notice that if f prime is equal to 0 here, if we consider the concavity of this is concave down. So my second derivative is less than 0. If I have a a 0 here, and my second derivative is negative, it has to be curving down. So the only thing that could happen is that this is a maximum. On the other hand, if I have a minimum here, then everything would be concave down. Okay, sorry. So we're greater than 0 here. My f prime at that point is equal to 0. I'm concave up, so the only option I have is that this is a minimum. And so that's what this is saying here. Before, we would check just with the first derivative. I would find my x's where I'm getting whatever value I'm getting a 0 for that value. Then I would check my first derivative. I would have to check both sides of this. But now all I have to do, that's the first derivative. Now what I would need to do is I consider the second derivative of this at this point. I don't have to check every interval. If I get a positive number there, I know that this is curving up. And so I know that this is a minimum value. On the other hand, if I got a negative here, I would know that this is happening. It's curving down. And so since I'm getting a 0 here, if it's curving down, it would have to be a maximum value. So using the second derivative test, we're just going to take our derivatives of this and see what happens. 3x minus 12. And then also consider the second derivative, which is 3. Notice this is always positive. And so it's always positive, so this is always concave up for the whole function. All of this is always going up. And so if I look back at the first part, I want to set this equal to 0 to find my critical points. 3x equals 12, x equals 4. So this is my only possible critical point. I could go back and check either side what's happening, whether it's increasing or decreasing. But now with the second derivative check, I'm just going to check the concavity of this. So I'm going to look at f double prime of 4, which We already know it's concave up, it's 3. So if this is concave up, and I'm getting a 0 at 4, this has to be a minimum value. And we know that because if it's concave up at that point, then it has to be concave on both sides of that point. And the only way for that to happen is for that to be a minimum point.